And unfortunately, you know, I don't have homework help from this unit, so you're going to need to ask me your questions if you have questions over these. Some of these were difficult algebra-wise, and some of these were difficult geometry-wise. So take time to check all of your answers, and then we'll work some of them. Okay, let's check the next set of answers, 22 through 33. Okay, so sorry, we're doing number 7. If PA is 15 and AR is 8, we learned yesterday when a radius meets a tangent line, you get a right angle. When a radius meets a tangent line, you get a right angle. So that one's Pythagorean theorem. 8 squared, So first you do Pythagorean theorem with 8 and 15, 8 squared plus 15 squared. I think you get 17, right? So this segment is 17. And it wants this segment right here. And so we would take 8 away from 17 because 8 is the radius. We did that exact one in our notes yesterday, just with different numbers. 14 and 15 is kind of different. We did not do one like this in our notes, so I'm glad you asked about this one. Here we go. So we know the length of those segments, and we want to find the length of DC. Now, what I am going to tell you is we cannot find the length of this, and we cannot find the length of this. We can't find the length of those individually, but we can find the length of DC. We know what they add up to, even though we don't know what they are individually. So, we're going to use that ice cream cone postulate again, and we actually get to be creative on this problem. How often in math do you get to be creative? So, we're going to take that 20, you just pick any of them, and we're going to divide it up however we want. Now, you could do 10 and 10, but I discourage you to do that because then you'll accidentally think that that's a midpoint, and it's usually not a midpoint. So I wouldn't split it up 10 and 10. We could split it up, let's say, 8 and 12. Do you agree that 8 plus 12 is 20? I just made that up. But the cool thing is, whatever you make up, you're going to end up with the same answer. Now we're going to use the ice cream postulate. If this segment is 12 and this tangent segment is 12. Then AB is 16, so 16 minus 12 would make this 4, and if this is tangent and this is tangent, then that one's 4. And then 12 minus 4 would give us 8. If this segment is 8, then this segment right here is 8. And also, if this one's 8 here, then this one's 8 here. It was just a coincidence that they ended up being 8 and 8 because of the numbers that I chose. Either way, x DC, or x, is going to be 16. It doesn't matter what you chose. When you work your way around, whatever numbers are left for DC, they will add up to 16. So that's how you do that one. So we're looking at 20 and 21. A lot of these on the back, you're going to use similar triangles, and you're going to use proportions. So you need to be comfortable setting up proportions. On this one, let's see, the radius of circle C is 15. So the 15 can go here and here. ED is a common external tangent. Okay, and then the radius of this one right here is 5. And you were asking about, so you already got x. You already got that this one is 24 because you were asking about 20 and 21. So we need to find y and we need to find z. So you could either use scale factor or you could use proportion. We know that this is 5 too right here, by the way. This one has such a pretty scale factor, 5 to 15, that's just being multiplied by 3. So we know that that smaller triangle is just a third of the larger one, so you can think of it that way if you want. You could also do when a radius meets a tangent line, you get a right angle. So Pythagorean theorem, 12 squared plus 5 squared, that'll give you 13. So you know that that's 13 right there. And if we know our scale factor is 1/3 or 3, then we can just take 13 and we can just multiply it by 3. So y is 39. Could we have set up proportions? 5 is to 15 as 13 is to y. Yes, we could have done that. But I'm using scale factor because it's pretty this time. To find z, we would just take this 39 and we would subtract this, minus this, minus this. And that would give us z. So we were using our radii to help us. The 5 was used twice and the 15 was used twice. So that would be a subtraction problem. Z was 26. Last problem that we're going to have time to look at today is 22 through 24. Same thing. So we have similar triangles. They're similar by angle, by the way, if you were wondering. They share this angle, and then when a radius meets a tangent line, you get a right angle. So this is a right angle, and this is a right angle. Okay, so we can use proportions, but we can also use something else. These two circles are tangent to each other. And so we know that this is 12 because it's a radius, and we know this is 8 because it's a radius. That didn't happen in like this problem down here because the circles are overlapping. But in this problem, the circles are tangent, so we now know RU. RU is 20. So that's a good starting point. We already know this. It is 20. Now we're going to use proportions to find our missing ones. Let's do this. 8 is to 12 as, if I call TU X, because that's the next thing I'm trying to find, so I'll call it X. I would say 8 is to 12 as X is to, and what would I put in the denominator there? Because this is where students get messed up. Good. So you don't put 20 there. You have to put X plus 20, okay? So 8 is to 12 as X is to, you have to use this whole thing, which is X plus 20. So you will cross multiply and you will do some algebra magic and you will get that TU is 40. So we now know TU, it's not X anymore, it is 40. The last part of this problem is a little ugly. So notice that we have this right triangle here. And we can do Pythagorean theorem. We can always use Pythagorean theorem with a right triangle. So we're going to do 40 squared minus 8 squared. Normally we give you pretty numbers. This one's not so pretty. So when you do Pythagorean theorem on that, what do you get for ST? It's going to be something root 6. That's what you did wrong. You already know. Okay, so you get the square root of 1,536, I believe. So you can simplify that. Do your simplified radical. And then, unfortunately, you have to do that same thing again with, this is 12, this is a right angle, and this is 40. And you have to do the same thing again with the 40. Now, when you reduce both of those radicals and then you subtract them, you will get 8 root 6. Okay? So like for ST, when you reduce that, it would be 16 root 6. And then for QT, I think you got 24 root 6. And so to get QS, you would just subtract those two. Not pretty. You could have used proportions once you found ST instead of doing Pythagorean theorem twice, so that's totally up to you. We do need to get started on today's lesson now. So title your notes. Oh, we're not doing that yet. Title your notes chords. We probably... Okay. So... a lot of these theorems, you're going to be like, that's common sense. But we're going to go ahead and say these theorems because we're going to be using them later throughout this unit, okay? So it might be common sense, but some people worked really hard to come up with these, okay? So I'm telling you that a radius is perpendicular to a chord. I am telling you that that is true. A radius is perpendicular to a chord. What symbols can we add to this picture? So we can add, obviously, the right angle marking. What do you think that radius does to that chord if it's perpendicular to the chord? No. Ooh, so Ganesh says he thinks it bisects the chord. And he's totally right, and we can take time to prove this. But anytime a radius is perpendicular to a chord, it bisects the chord. Let me show you what it would look like. There's an example of a radius that is not perpendicular to a chord. See how when they're not perpendicular, that radius is not cutting that chord in half. This segment is different from the other segment. But when a radius is perpendicular to a chord, it goes through the chord's midpoint. Now, does the chord bisect the radius? No. So let me show you something cool. As long as this chord is perpendicular, I can drag it up and down. It goes through the middle, goes through the middle, goes through the middle. But the radius does not get cut in half. It's only the chord that gets cut in half. Okay, so this is what you would write down. This is the first theorem. In a circle, a radius that is perpendicular to a chord bisects the chord and its arcs. The converse is also true. Oh no. Sorry about the spacing there. The converse is true as well. If a radius cuts a chord in half, then it's perpendicular to the chord. So it's true both ways. Okay, so what else are we going to learn about chords? If I tell you that two chords are the exact same distance from the center, what do you think is true about the length of those two chords? Good. So here's the reasoning or the logic here. If I draw the diameter of a circle, that is the longest chord. That is the longest chord I can possibly draw. But as the chords get further and further away from the center, they get shorter and shorter and shorter and shorter. So if these are the same distance away from the center, then they're the same length, because the further you get from the center, the shorter you get. So if they both traveled, let's say 3 inches away from the center, then they must be the same length. Okay? So that's the next theorem of the day. Chords that are equidistant from the center are congruent. Of course, the converse is also true. Congruent chords are equidistant from the center. Did I tell y'all what was happening with, I updated Smart Notebook, and they have a bug in their update, so they don't like when I change colors in a sentence. So notice a lot of times when I change colors, there's not a space there. So I have to double click on it, like open the text box, for them to put the space back in. See the R in the equidistant? So you're going to have to just be patient with that, because I can't double click this because it has a disappearing box over it. So anyways, so the converse is true. If two chords are congruent, then they're equidistant from the center. So all of these are called biconditionals. The original and the converse are both true. Still more theorems to go. What can we conclude about arc AB and arc CB? So let's take a look and draw some conclusions from our picture. I'm sorry that I'm just telling you everything that you're supposed to be drawing conclusions about. But segment AB, that chord, is congruent to chord CB. So what do you think is true about the arcs that they intercept? Let me use that word. Intercept. So if the chords are congruent, don't you think we could conclude that the arcs that they intercept are congruent? So if those arcs are congruent, that would mean that they have the same length and they have the same degree measure. Remember, there's two things true about every arc. And so if this is like, if this is an 150 degree arc, then this is a 150 degree arc. So the theorem is congruent chords intercept congruent arcs. Congruent chords intercept congruent arcs. See how I told you a lot of these are just like common sense? You're like, you didn't even have to tell me that. I probably could have figured that out on my own. But we're just documenting it because now that we've named these theorems, now we can use them in all of our future stuff. Now that we know we're not just guessing, it's a real theorem. It's on the calendar. All right, now we have 3 brand spanking new theorems. Let's try them out. Okay, segment NP is a diameter of circle Q. Okay, so we learned that when a radius is perpendicular to a chord, it bisects the chord. So this is a radius, and it's perpendicular to a chord. So I am allowed to conclude that MR is 11. If I'm concluding that MR is 11, then I can conclude that MO is definitely 22. All right, so likewise, remember if the radius is perpendicular to a chord, it's not only going to cut that chord in half, it's also going to cut the arcs in half. So MN is 65 and NO is also 65. Arc no. There we go. MP. Now we're going to use our diameter to help us out with MP because we know in a semicircle there's 180 degrees. So if we take away in M, we will be left with MP. Oops, sorry. It's redundant to put a degree symbol when you have this M because you're already saying the measure, and so you don't put a degree symbol because that's redundant. We did that in the angles unit. Last one, OMP. Almost sounds like OMG. OMP. O to M to P. It's a clue right there when they use 3 letters that your answer is going to be a major arc. Your answer is going to be greater than 180. So that's a clue that you go the long way around, not the short way around, obviously, because you have to go through M. So this is just arc addition. It's just, 65 plus 65 plus 115. Or you could do 180 plus 65. Yep, 245. Keep going. Good job. Find X and Y. So first of all, we can find X very easily. We know when a radius is perpendicular to a chord that it bisects the chord. So we can do this one very easily. So X is 9. But what about Y? Now, Y, by the way, is the distance from here to here. You always go from intersection to intersection. So Y was not asking for the radius. It's asking for that distance that I just showed you. You go until you see the next intersection. Any ideas? Klein said Pythagorean theorem. You have to get creative here. You have to draw another radius of your circle. Good. So when you draw a radius, now you have a right triangle. This is 9, and that one's 41. Good job. So you had to get creative there. That segment was not drawn for you. And that is one of our triples. So not drawn to scale, right? This picture is not even close to drawn to scale. Sorry about that. So Y is 40. Okay, so that was a little trick of the trade. You got that one? Good. A chord is located 5 inches from the center of a circle with radius 13 inches. Find the length of the chord. I purposely covered up the picture because you need to be able to draw these on your own. So try drawing a picture of that situation. So here's the picture. It's located 5 inches from the center. So that's the location. You draw a perpendicular segment. That's how far away you are from something. And the radius of the circle is 13. I would draw this radius instead of drawing, I would not draw this radius because that purple radius is not really going to help us at all. And then the answer is glaringly obvious once you have the right picture. It's a Pythagorean triple. This is 12. Find the length of the chord. Well, if the radius is perpendicular to the arc, then it bisects, not the arc, perpendicular to the chord, bisects the chord, and so the chord is 24. Is that good? Okay, this is the last thing. We called it an exit ticket. I just want to go over how you would approach this. The only thing I want you to see in this picture is that the further away you get from the center, the shorter the chord, right? So what would be the longest chord there? Longest chord. DG. So the longest one is DG, because that's the diameter. That's as long as you can get. Now, what would be the second longest? The one that's the closest to the center, BF. Now, These two, it's kind of hard to tell which one is further away from the center. So that's when we're going to use these right here. AC is 100 and EC is 90. Now, congruent chords intercept congruent arcs. So the chord is, its length is kind of proportional to its arc. It's related at least, if not proportional. So anyways, the longer chord is going to have the larger measure of its arc. So AC would be the longer one because its arc has a bigger measure. And then EC would have been the shortest chord in the picture based off of the information we were given. Okay? All right.